Hi, this is Calculus 12, Chapter 6.1. We're going to be looking at antiderivatives and the slope fields. And the definition, slope field or direction field for the first order differential equation, we abbreviate this dE, dy dx equals f of x and y, is a plot of short line segments with slopes f of x comma y for a lattice of points x, y in the plane. So this isn't as complicated as it sounds. So basically, we can find the slope anywhere for the function. And if we have an initial starting point, we find a particular function. So in this graph, we have y being vertical and t being horizontal. So if we have the differential equation, dy dt equals 0.056y, the initial condition and this happens to be the y-intercept because we're doing y of 0, equals 100. And we have to think back. Similar to y equals negative 2x plus b, there's an infinite number of solutions here. But if we pick a special b as our initial point, then we get a specific solution. Okay, so here is our general solution. Because this is the antiderivative of this. Okay, and to get a specific solution, substitute initial condition, solve for c, and substitute back. For specific solution. Okay, so the answer to this, the specific solution, is 100 times e to the power of 0.056t. Okay, we have another definition, the indefinite integral. So you've been doing definite integrals. This is an indefinite integral. The set of all antiderivatives of a function, f of x, is the indefinite integral of f with respect to x and is denoted by the integral of f of x dx. Recall, we looked at antiderivatives in chapter 4.2. We had capital F prime of x equals f of x, and if f prime of x is equal to g prime of x, then f of x is going to equal to g of x plus c. So the integral of f of x dx equals capital F of x plus c. And c is called the constant of integration. And we say indefinite integral of f with respect to x is f of x plus c. Okay, here we have a table of indefinite integrals, and we also have the corresponding derivative rule. Okay, so here's just the power rule for integration. Here's the power rule for differentiation. The integral rule for 1 over x, which is ln x, and the differentiation rule for ln x. And here we have one for exponentials. Here we want to have one for the trig functions. And I want to add a few more. And if you look at the appendix section of your book, you'll see some more antiderivatives. And number 6, the integral of 1 over ax plus b. And that's ln absolute value of ax plus b all over a plus c. And I'm not going to read these out for you, but we have the a coefficient. And it's useful if you have this table in your reference sheets. And please note that 2, 3, 4 have the additional coefficient k's. So let's take a look at some examples. Integral of x to the power of 3 over 4 dx. We just use the power rule. That's number 1. So this is x to the power of 7 over 4. We add 1 to the exponent. We divide it by the new exponent plus c. And we can simplify this by multiplying by the reciprocal over 7, x to the power of 7 over 4 plus c. Here we have the integral of 1 over the 5th root of x. And this is just number 1 again. And whenever you see a root like this, it's better to rewrite it as a power. So that's x to the power of negative 1/5. And we make it negative because this is in the denominator. So we add 1, x to the power of 4 over 5 over 4 over 5 plus c. Again, we want to remove the fraction in the denominator. So we multiply by the reciprocal. We get 5 over 4, x to the power of 4 over 5 plus c. Next, we have an exponential. It's an exponential because we have x in the exponent. So this is number 2. So the integral of the exponential is just the exponential. And this has the chain rule built in, so it's negative 5 over 2 plus c. Again, we don't want a fraction in the denominator. Negative 2 over 5 e to the power of negative 5 over 2x plus c. Moving on, this is a trig function. We're using rule number 3. And this is negative cos x over 4. We have a coefficient of 1/4. So we have to put 1/4 in the denominator and plus c. Again, we want to simplify this. Negative 4 cos x over 4 plus c. Now this is important. As I said before, you need to have the plus c or you'll lose half a mark on the question. Okay, you should try these two on your own. So pause it now and then come up with a solution and check your answers. Okay, and we're back. This is x to the power of negative 1/3 dx. So this is x to the power of 2 over 3 over 2 over 3 plus c equals 3 over 2 x to the power of 2/3 plus c. Again, we're using number 1. Here, we're using number 4. So we have sine 5x over 5 plus c. You can leave it like this, or you can write 1/5 sine 5x plus c. Okay, just a reminder, trig functions only take one term. So 5x is your parameter. So it's implying that it's this plus c. It does not imply this. Okay, that's two terms. Properties of indefinite integrals. Let k be a real number. We have the constant multiple rule. So k times f of x dx equals k times the integral of f of x dx. If k is -1, then we have the integral of negative f of x dx equals negative the integral of f of x dx.
Recall.
And just like with derivatives, we have the sum and difference rule, integral of f of x plus or minus g of x dx equals the integral of f of x dx plus or minus the integral of g of x dx. So let's look at an example here. We have the integral of e to the 2x minus sine x over 3 minus x squared dx. So we'll use the sum and difference rules. We have the integral of e to the 2x dx minus the integral of sine x over 3 dx minus the integral of x squared dx. Now we just integrate each one. So this is e to the 2x over 2. And technically we have a constant term here, minus negative cos x over 3 over 1/3 plus c2 minus x over 3 over 3 plus c3. And we can combine these constant terms into one constant term. So we have 1/2 e to the 2x. There's two negative signs, so that's plus. This 1/3 becomes 3 cos x over 3 minus x cubed over 3 plus c. Okay, solving separable differential equations. These are equations that we can isolate one variable to the left-hand side and the other variable to the right-hand side. Then integrate both sides. So here's an example. Find the displacement function given v is ds over dt, a equals dv over dt, and that equals negative 9.8 meters per second squared. And we're given some initial conditions. V of 1 equals 100, S of 2 equals 20. We know that V prime, t, is the acceleration. That's dv dt, and this is negative 9.8. So the trick here is use highest order derivative. Acceleration is the highest order derivative. So we want to separate this. dv equals negative 9.8 dt. And then we want to integrate both sides. Separate and integrate. So now we have v equals negative 9.8 t plus c. Okay, basically here we're integrating 1. And if we're integrating 1, it becomes v. Now we need to substitute to get our specific solution. V of 1 equals 100 equals negative 9.8 times 1 plus c. We want to substitute initial condition. So C1 equals 109.8. So V of t equals negative 9.8t plus 109.8. That's the first level. Now we need to do the second level. S prime of t equals ds dt equals negative 9.8t plus 109.8. And we want to use next highest derivative. So we want to separate and integrate. So ds equals negative 9.8t plus 109.8 dt. And we want to integrate. So we have s equals, and integrating the right side, we get negative 9.8t squared over 2 plus 109.8t plus c2. Now we substitute our initial condition, so we have s of 2 equals 20 equals negative 9.8 times 2 squared over 2 plus 109.8 times 2 plus c2. Simplify this a bit, we get 20 equals negative 19.6 plus 219.6 plus c2, and c2 equals negative 180. We substitute this back into our function, so we get s of t equals negative 4.9 t squared plus 109.8 t minus 180. And that is the displacement function that we are looking for. We can check our solution on a graphing calculator. This is 0. This is our s of t. This is our v of t. We can tell because this is linear and this is not linear. And s of t is not linear, whereas v of t is linear. Okay, so we have s of t here, we have v of t here. And we look at s of 2. That equals 20. That matches our initial condition. We have v of 1 equals 100. And that matches our initial condition. And that completes this lesson.